Hello everyone, welcome back to Mini Courses Episode 4. I'm Irene, a member of the G11N SIG of openEuler community. In a previous episode, we introduced some commonly used crash utility commands. There's one more category, the system state related commands. Most of the crash utility commands come from this set of kernel-aware commands, which delve into various kernel subsystems on a system-wide or per task basis. The first one is BT, arguably the most useful crash command. BT displays a task's kernel stack backtrace, including full exception frame dumps. BTA displays the stack traces of the active task on each CPU. BTL shows file and the line number of each stack trace text location. BTF displays all stack data contained in a frame. Similar to the BT command, another frequently used command is log, that dumps the kernel log buffer, which often contains clues leading up to a subsequent kernel crash. In this stack trace screenshot, it shows what the bug is, where it occurs, and the oops error code. The oops error code can be converted into bit code. This table lists some brief description of each bit code that help you understand the crash. Other commonly used commands in this category include dev, which displays data concerning the character and block device assignments, I/O port usage, I/O memory usage, and PCI device data. Files, which displays the task's current root directory and working directories. And then for each open file descriptor, it shows its file struct address, its entry struct address, its inode struct address, the file type, the file's full path name, IRQ, which displays data concerning interrupt request numbers and bottom half handling, kmem, which displays information about the use of kernel memory. This command has various options that delve into the state of several kernel memory subsystems. In this example, kmem-s is used to display all slab data, including all slab objects and whether each object is in use or not. Mod, which displays the list of currently loaded kernel modules. More importantly, it loads the debug data from the module object files if they are available, allowing symbolic debugging capability of kernel modules. Mount, which displays basic information about the currently mounted file systems. Net, which displays various network-related data. For example, NetA displays the ARP cache, and NetS displays open network socket SOC addresses, their family and type. And PS, which displays process status for selected or all processes in the system. It's a useful process status command in typical Linux PS command type output. Now let's use a simple case to explain how to use the crash utility to locate faults. In this case, a null pointer is constructed for the tunnel driver in order to cause a kernel panic. After the system panics, we invoke the crash utility and use the BT command to get the kernel stack backtrace. The output contains the exception RIP, tunnel get drive info plus 55. Then, through the log command, we see the stack process and find that the s2 get drive info function is triggered when dev IO control is invoked. When this function executes the tunnel get drive info instruction, an error occurs at hexa 37 offset of the base address. Also, in this command output, we see the bug message, which says that the system is unable to handle kernel null pointer difference at hexa 804. From the BT command output, we know that the exception occurs with the address offset of 55. So the plus 55 and plus hexa37 actually refer to the same address? Well, using the bt and the log commands, we get the basic information about the stack on the core where the panic occurred. Then we use the mod s command to load the module information and use the disl command to disassemble the faulty pointer to understand what happened. In this command output, we see that the error occurs around line 2401 when the driver executes an instruction to move hexa 804 into the EAX register, and access to hexa 804 is suspended. In the code, we see that at line 2404, the system tries to access the tunnel flag. However, the tunnel has been set to null in advance. We can see that at line 2403, which means the address of the pointer is void. Then we run the struct ox command to determine whether the 804 address represents the flags, a structure member. In the command output, it is found that hexa 804 does represent the flags. Therefore, when this structure member is accessed, actually the hexa 804 void address is accessed, and a problem occurs as a result. Through this simple case study, we now understand basically how the crash utility is used to locate kernel faults. That's all for this course, and hope you'll find this helpful. Thank you for watching. If you are interested in Linux kernel or openEuler OS, please visit our SIG page and stay tuned for more mini courses. See you next time!